For the second talk of today's session, we're happy to listen to Houcine Ben Dali from Paris-Cité and
Université de Lorraine.
Nancy. So from Paris and Nancy, who will tell us about differential equations for the series of hypermaps with a control on their full degree profile. So Houcine, the stage is yours.
Thank you, Ariane, for the presentation and for the opportunity to give this talk. So I will talk about this differential equations of one parameter deformation of the series of hypermaps in which we control the degrees of vertices, faces, and hyperedges. So this is what the equations look like, and I will try to explain what are the different objects which appear in this equation. So in the talk, so basically this series G alpha is a one parameter deformation of the series of hypermaps. So when we take alpha equals 1, we obtain the series of orientable hypermaps, and for alpha equals 2, we obtain the series of all hypermaps orientable or not. And the CL is some differential operator, which is the same case as the operators that Victor was talking about in the previous talk. And then I will try to explain very briefly the proof of these equations. First, an algebraic proof which works for any alpha, which is related to Jack characters, and then a second proof which works for alpha equal 1. So this is precisely the case of orientable maps. So I will start by defining hypermaps. So what I'm going to say is works exactly the same for bipartite maps, which are just the dual of hypermaps. But for the combinatorial proof, it will be more convenient to work with hypermaps. So I will try to recall some definitions that Victor already gave, but maybe a little bit differently. So another way to define maps is we start first with connected maps. And we say that a connected map is just a connected graph which is drawn on the surface, orientable or not. And the goal will be to count connected maps up to homeomorphism. So we have here two examples of connected maps. So the first one is planar, so it's just drawn on the plan, or we can draw it on the sphere without intersections of the edges. And the second example is non-orientable, and it's drawn on the Klein bottle, a non-orientable surface of genus 1. So here the square represents the Klein bottle. So as in Victor's talk, we should glue the edge of the square using these arrows, and then inside of it we have the map. And then so this is the definition of a connected map, and more generally we say that a map is a collection of connected maps. So, for example, you can consider the map which contains these two connected components. And we say that the map is orientable if all the connected components are orientable. They are drawn on orientable surface. So here, this map of with these two connected components is not orientable because it has one connected component which is drawn on a non-orientable surface. And then a hypermap is a map for which the faces are colored in two colors, which I will call plus and minus. And I will always represent the minus faces with the blue they are colored in blue in my pictures to see them easily. And the condition that we put is that an edge should separate two faces of different colors. So we cannot have an edge which is incident to two faces of color plus or two faces of color minus. And usually one of the two colors that we call them the faces of the hypermap, and the other one are the hyperedges of the hypermap. And here to see the symmetry of the problem, I prefer to use these colors plus and minus. So now we have a map, and we will consider generating series. So we'll try to keep track of some information about the map, and this the first information that it's natural to think about the size of the map, which will be also the number of edges, and we'll denote it with these bars. So here we have a map with 12 edges, so with size 12, and then we can try to also to have more information about the map by assigning to it partitions, integer partitions. So a partition is a decreasing finite sequence of integers, and we say that a partition lambda is a partition of n if the sum of the entries of lambda gives n. So as in the talk of Victor, we can define many partitions. The first partition, we call it the vertex partition, which contains the information of the degrees of the vertices of the map. So you can notice that in the hypermap, the vertex has always even degree, because when we turn around the vertex, colors plus and minus alternate. So what we will do is to take all the degrees of the vertices, divide them by 2, and then reorder them to obtain a partition. So for in this case, we have this a vertex partition. So here, for example, we have a vertex of degree 6. So we divide by 2, so we obtain this part 3 in the partition. Here we have a vertex of degree 2, we divide by 2 and we obtain a part 1. And we do the same for all the vertices to obtain this partition. And then you can do the same thing with faces. So if you start with the plus faces, we can just take the degrees of all plus faces and then reorder them to obtain partition, which we call the lambda plus. And we do the same thing with minus faces, and we obtain the third partition, lambda minus. And the first thing that we can remark is that these 3 partitions have the same size, and this size corresponds exactly to the size of the map. So it's 0, 12. And we can consider the triplet of the 3 partitions, and we call it the profile of the map. So now the idea would be to consider the generating series of maps in which we control all this information, so the size and the 3 partitions. So if you want to keep track of this information, we need to use variables. So the first variable t will keep track of the size of the map, and then we have 3 alphabets of variables, pi, qi, and ri, which correspond respectively to vertices, plus faces, and minus faces. So more precisely, the weights that we will consider in the generating series is are the following. So to an edge, we associate the weight t. To a vertex of degree 2i, we will associate the weight pi. And to the plus face of degree I, we will associate the weight qi, and we do the same for plus and the alphabet ri. And then we will take the product over all edges, vertices, and faces. So if we denote p lambda as the product of all the p lambda i's, the weight that we will obtain for hypermap M is t to the power of the size of the map, p indexed by the vertex partition, q indexed by the plus partition, and r indexed by the minus partition. And then we can define generating series. So these generating series, they depend on this alphabet, on these 3 alphabets, P, Q, and R, and the variable t. So the first alphabet, I will denote it H1. It corresponds to the first generating series is H1, and it will correspond to orientable hypermaps. And the second one is H2, and will correspond to all hypermaps, orientable or not. So here there are some normalization factors which appear Z and with some powers of 2. And actually these are related to some labeling of the maps, which we use to eliminate symmetries. So when we count maps, we don't really like symmetries. So we root some corners, or we label some vertices. And these factors are related to the labeling that I'm not explaining here in detail here. So what do we know about this generating series? So this specialization that Victor already explained, maybe even in a more general setting in his talk, is the specialization in which we keep two alphabets P and Q, and then we specialize the third alphabet. So the specialization works as follows. So we replace all the RJs by one single variable U. And combinatorially, this means that we are keeping these two alphabets, so we keep track of the degrees of all vertices, the degrees of all plus faces, but for minus faces, we only keep track of the number. So we have here, in this way, U to the power of the number of minus faces of the hypermap. And when we do this specialization, so these are very known, very well studied generating series. And in particular, when alpha, so when in the orientable case for H1, this series is known to satisfy equations of the KP and the two-towed hierarchy, and in the non-orientable case, the BKP hierarchy. And yes, as Victor explained, so we have equations for, in the orientable case, we have equations for the non-orientable case, but we do not know if there is some interpolation between the two of them, if there is an equation which unifies the KP and the BKP equations. So what Chapuis and Dołęga did is that they proved that there exists some alpha deformation, so some deformation in one parameter which gives the orientable series for alpha equals 1 and the non-orientable series for alpha equals 2. And this deformation is defined using Jack polynomials. And they proved that with this deformation, we have differential equations. So here on the left-hand side, you have a derivation with respect to the variable Qn. And on the right-hand side, we have these differential operators Bn that Victor defined. And I will go back to this later. So the question now, what can, so we understand pretty well this specialization of the generating series, but what can we say about the generating series in which we keep the full profile, or the three alphabets P, Q, and R? So there is this known result that this can actually be expressed using symmetric functions. So in the orientable case, the generating series can be written using Schur symmetric functions, and this is related to the representation theory of the symmetric group. And in the non-orientable case, this is related to the generating series can be written using zonal polynomials, and is related to the representation theory of a Gelfand pair of the symmetric group and the hyperoctahedral group. The only problem of this approach is that it is quite rigid. So, for example, we do not know if there is a deformation of this. So we cannot use this approach to understand the alpha deformation related to Jack polynomials. And also, it does not really give information about the recursive information about maps. So it does not give us differential equations like this. So it is natural to ask if there is a differential equation satisfied by this series with full profile controlled, and this is the question that I will try to answer in this talk. So the first thing to do is I will try to define a slightly more general generating series. So in this generating series, HIs with three alphabets P, Q, and R, they are homogeneous in the three alphabets. So the power of the total power of in the alphabet P is the same as the alphabet Q and the alphabet R. So we start by relaxing a little bit this condition by considering some hypermaps with marked faces of degree 1. So what we'll do is each time we have a hypermap, we can decide to mark some faces of degree 1. With only condition that whenever we have an isolated loop, and what I mean by isolated loop is a connected component of the hypermap, which contains exactly one vertex and one edge. And by definition of a hypermap, this connected component should have two faces. One is colored minus, and the other one is colored plus. So if we try to mark faces, a priori we have 4 ways to mark these faces. So for the plus face, we can decide to mark it or not, and for the minus face, we can decide to mark it or not. Except that we prohibit one of the cases, which is the last one, where we mark the two faces. So at the end, we have 3 cases which are allowed, and the 4th one is prohibited. And so this is a kind of technical condition, but it assures that we will not have edges in the hypermap which are incident to 2 marked faces. So we can check that this is the only case where in which we can have an edge incident to 2 marked faces. Let's take an example. So we have here this map which has 2 faces of degree 1, this minus face and the plus face here. We can decide, for example, to mark this one and not this one. So now we know that when we have a hypermap, we have a profile, which is 3 partitions of the same size. We can now assign a profile for these hypermaps with marked faces. So how we define it? So we start from the profile of the original hypermap, and then each time we mark a face, we go to the associated partition in the profile, and we just delete one part of size 1. So for example, here we have marked the face, a minus face. So we go to the partition lambda minus, which is the 3rd one in the profile, and we just delete one part of size 1. So is this definition clear? Okay, so except that now the profile does not contain 3 partitions of the same size. So how do we define the size of the hypermap? So we have this quantity. So we take the sum of the size of lambda plus, lambda minus, and then we subtract the size of the lambda vertex. And we can check by an easy argument that this size corresponds to a number of edges in M which are not incident to a marked face. So this means that here, for example, we marked one face. So this edge, which is incident to this face, will be just not counted in the size. So now we have a definition of new definition of size and profiles for these hypermaps with marked faces, or more precisely marked faces of size 1. So we can define a new generating series, and which we denote with this tilde. So H tilde 1 will be generating series of orientable maps, but with marked faces. And then we use the definition of size and profile just defined the previous slide. And actually, it's easy to see that we can obtain H1 from H tilde 1 just by taking the homogeneous part of this generating series. So if I just look at the monomials for in which are homogeneous in the 3 alphabets P, Q, and R, we'll just have the H1 because this corresponds to hypermaps without any marked face. But we can also prove that we can obtain H tilde 1 from H1 by applying some exponentials. So this is a kind of inclusion-exclusion. So we just have an exponential of we multiply by P1 or we derive by Q1 or L1. So I'm saying this just to say that if we understand the recursive structure of H tilde 1, so we also understand the recursive structure of H1. So now we can do the same thing with for non-orientable maps, and we can define H tilde 2 as a series of hypermaps with marked faces of degree 1 and which are orientable only.
So I just have a possibly silly question about the fact that the homogeneous part of H tilde 1 gives you H1.
Mm-hmm.
If you have the same number of plus marked faces and minus marked faces, it counts in the homogeneous part of H.
No, because if you imagine here, for example, that we have marked this minus face and this plus face. So what we will do is we lose one here and we will lose one here.
So it's still not equal to the size of the degree partition. The vertex partition.
Exactly. Okay, so we have lambda plus and lambda minus have the same size, but they do not have the same size as lambda.
Yeah. Okay. Great. Thank you.
So okay, so this finishes the first part about the definition of this generating series that we are looking at. So this series G alpha, which appear in the main result, is actually alpha deformation of the series H tilde 1 and H tilde 2. So now I will talk about the differential operators. This differential operators CL alpha, which are more or less they were defined in the talk of Victor. So I'll try to explain how they act on maps. And for this, I will need bipartite maps, which are just maps with this time colored vertices and not faces, and such that each edge connects two vertices of different color. So this is an example of an orientable map, orientable bipartite map. And as for hypermaps, you can associate weights to bipartite maps, and I will use just this weight, which keeps the information of the size of the map and the degrees of faces, only faces. So we just forget about white and black vertices. And when I say degrees of faces, so we look at the degrees of the faces and we divide by 2, because this is a bipartite map, so all faces have degree 2. And actually, there is this idea of using differential operators to act on maps. So we can translate some operation on maps using differential operators which act on the weights of the maps. So for example, here, if we fix a bipartite map M and we act on the weight or the face weight of this map by this operator, what we will obtain is the sum of all maps obtained by adding a white leaf on a black corner. So this means that we choose a black corner on the map and we add a vertex, a white vertex. How do we understand this? So we have this, first we have to pick a face which has some degree 2i. So this corresponds to the derivation with respect to pi. And then within this face, we choose a black corner. So we multiply by I. And then the face obtained will have degree 2i plus 2. So it corresponds to p indexed by I plus 1 here. And we can do more complicated by adding one edge between two existent corners of the map. And here, as Victor explained, we have many cases. So either we add an edge between two corners of the same face. So we start from a face of degree, or degree divided by 2, I plus j minus 1. So this corresponds to this term. And then we form two faces of degree I and j. And then you do the same if the two corners are not in the same face, or we choose two corners in the same face, but we add a twisted edge to form just a new face of degree I plus 1. So these operators, they encode perfectly all the ways of adding an edge to a map, but actually we can do better if we use these operators introduced by Chapuis and Dołęga, which allow to add one vertex. So they do not just add some edges randomly, but they add all the edges which are incident to one vertex. So what does this mean more precisely? If we start from a map M, which I represent with this yellow here, and we will act by CL when we act by this operator CL for alpha equals 1, we will add some vertex V and L new white vertices, which I denote W1, W2, WL. So this new black vertex can be connected to some old white vertices in the map. But the new white vertices are only connected to V. And this, what is interesting here is that these operators, they act nicely on maps, but they also have some differential expression, which uses catalytic, an extra alphabet, which we call catalytic alphabet. And the reason is that we want to add some edges, but on a precise corner, which we call the root corner. So in these intermediate steps, we would like to keep track of the degree of this root face. So instead of assigning a weight pi to the root to a face of degree I, to the root face, we associate the weight yi. So we add the n edges, So here, yes, we add some edges, and then by the end, we just forget that we have the root by applying some operator theta y. So this alphabet of variables yi's, they just appear in intermediate steps, and they're forgotten by the end. And that's why they are called catalytic alphabets. And this is precisely the kind of operators which appear in the differential equations here. So I still have not defined this dual of CL, but I think that it will come in few minutes. And so here we have the definition of this operator CL, and now we try to define this alpha deformation G of the generating series. And the definition will be algebraic using Jack characters. So I will not give the precise definition of Jack characters, but only the information which are interesting for this talk. So basically, Jack characters are defined as the coefficient of Jack polynomials in the power sum basis. And from what Victor explained in the previous talk, they are by this definition, one parameter deformation of the characters of the symmetric group. And they have also very nice properties. So they have a structure of shifted symmetric functions, and they are also a basis of the space of shifted symmetric functions. And what interests us today is that these Jack characters actually count maps, and more precisely a class of maps that we call layered maps, with some non-orientability weights, as the one that Victor was explaining. And this is the result that we obtained recently with Maciej Dołęga. So we established a differential construction of the Jack characters with this operator CL. And since we know that CL, they construct maps, so we deduce that the Jack characters, they count maps. And this formula is for alpha equals 1. It corresponds to a formula for the characters of symmetric group, which has been conjectured by Stanley and proved by Valentin-Ferré. So, as I said, these Jack characters, they form a basis, an algebraic basis of, a linear basis of some space called the space of shifted symmetric function. So it makes sense to understand the structure coefficients. So these structural coefficients are defined as follows. So we take two characters, theta mu and theta nu, we multiply them. So we know that the product of the two of them is still a shifted symmetric function. So it makes sense to expand it on a basis of the shifted symmetric functions, which is the same basis of Jack characters. And the coefficients which appear, we call them the structural coefficients. And they are indexed by 3 partitions, pi, mu, and nu, with some condition on the sides. So why are we interested in these structural coefficients? Because we have a theorem which says that this coefficient, when alpha equals 1, give the number of orientable hypermaps with marked faces, and which have the profile pi, mu, and nu. And when alpha equals 2, it gives also the number of hypermaps, but this time orientable or not, and with marked face and the same profile pi, mu, and nu. So if you remember from the talk of Victor, he talked about this Golden-Jackson conjecture called the matching Jack conjecture. So actually, when we take the special case when the 3 partitions pi, mu, and nu have the same size, this corresponds to the coefficient C of the matching Jack conjecture. So this is kind of a slight generalization of these coefficients, and by the end of the talk, I will tell you about a generalized conjecture related to these coefficients. So, in particular, if we define a series G alpha, which contains these structural coefficients G, we know that when we take alpha equals 1, this will correspond to the generating series of hypermaps, orientable hypermaps with marked face. And for alpha equals 2, it gives hypermaps orientable or not. And the main theorem is that this series is satisfies the differential equation using these operators CL. And here, CL dual is a dual in the sense of a product of a scalar product on the space of symmetric functions, which is an alpha deformation of the whole the scalar product. And it's basically saying that we want that the power sum symmetric functions are orthogonal.
So in some sense, it's the adjoint operator?
Yes, exactly, yes. Okay. It's the adjoint operator with this scalar product. So in order to prove this differential equation, what we do is we start by the fact that we know how to construct Jack characters using this differential operator CL. And we know that these coefficients G are structural coefficients. So they are completely characterized by the Jack characters. If we know all the Jack characters, we should be able, in some sense, to extract information about the structural coefficients. So we write that we have a differential construction of Jack characters using the operator CL, and then we try to decompose this equation. So at first we have many layers, which is related to this combinatorics of layered maps. So we have many exponentials here of C infinity. We try to keep exactly one exponential, and then we take some logarithm or some logarithm of operators to obtain just one CL here. And actually, these equations, they fully characterize the generating series G alpha. So this is it was very briefly the algebraic proof of this theorem. And the next part, I will try to explain how to obtain a combinatorial proof of this theorem, but only for alpha equals 1. Because we know that for any alpha, the operator CL has some combinatorial interpretation on maps. And for alpha equals 1 and alpha equals 2, we know that G alpha has a combinatorial interpretation. So it makes sense to try to understand this differential equation directly on maps.
Houcine?
Yes.
Just in your definition of C infinite, there's no U on the right-hand side, so where should it be?
Yes, sorry, yes, thank you. So it should be U to the power L.
Okay, yes, thank you.
So U is, when we think of these operators as by their action on maps, so CL adds one vertex, one black vertex with N new white vertices. And on the left-hand side, U is the number of, it keeps track of the number of white vertices that we have. So it should be U to the power N. Thank you. So before giving the combinatorial interpretation or the combinatorial proof for alpha equals 1, I would like to talk about commutation relations. So it's just a reformulation of the main result, but instead of seeing it as a differential equation on the series of maps, we will replace this series G alpha by an operator G alpha. So how does this work? So the series G alpha is depend on the parameter T and 3 alphabets P, Q, and R. So we define an operator G alpha, which goes from the space spanned by the alphabet P. So it's spanned by the monomials are P indexed by pi for some partition pi. And it goes in a space which contains the 2 alphabets Q and R. And the parameter T. And it sends the monomial P indexed by pi to this sum here. So it's a sum over mu and nu, which index the monomials Q and R, and the coefficients which appear in front are the coefficients G. So somehow this operator contains exactly the same information as this series G, except that it gives another approach or another way to think of maps, which is more dynamic in the sense that we will now think of it as a real operator which acts on something. So in the same sense of the operator CL, which act on weights of maps, for example. And it is not very hard to prove that the differential equations from the previous slide are exactly equivalent to the following commutation relations. So what do these equations say? So they say that it is equivalent to start by applying the operator G alpha. So we start from this space on the left here. We apply G alpha to go on the space with the alphabets Q and R. And then in this space, we will apply the operator CL in the alphabet Q plus CL in the alphabet R. And this is exactly the same thing as applying the alphabet CL first in the space of the alphabet P, and then go to the other space by applying G. And these commutation relations are equivalent to the differential equations. So giving a combinatorial proof for this commutation relation is giving a combinatorial proof of the differential equation. So what is missing here for this combinatorial proof is that, so we know how the operators CL act on maps, but we do not know how the operators G act on maps. So even for alpha equals 1, we know that the coefficients G, these coefficients in the three partitions, they count hypermaps with some marked faces, but we would like to understand the action of G as an operator. So this is the first step for the combinatorial proof, and for this we require, we will use a more general class of maps, which in some sense contain hypermaps and bipartite maps. And this class is given by bipartite and colored faces maps. So what does this mean? So it's bipartite really bipartite in the sense that each edge connects two vertices of different color. But we just have colors on faces. We do not require that an edge separates two faces of different colors. So in particular here we have many edges which are incident to two faces of color class. And since we are talking about the case alpha equals 1, so all maps are orientable. And in particular, since the maps are orientable, we have a sense of direct orientation. So we can define a direct orientation of all faces. And whenever we have a bicolor edge, so this is an edge we see which is incident to two faces of different colors, we can distinguish these faces in two types, edges of type 1 and edges of type 2. So how to define these types? We travel along plus faces in the direct orientation. So if you just traveling along the face and we see this edge, we first see the white vertex and then the black vertex. We will say that this edge is of type 1. And if we see first the black edge, if we see first the black vertex and then the white vertex, we will say that the edge is of type 2. So now the idea is that we have a combinatorial interpretation of the coefficients G in terms of hypermaps, and we try to understand them in this class of maps of bipartite colored face maps. So we start with a hypermap with some colored faces of degree 1. So we want to interpret this using this bipartite colored faces map, except that for now we only have black vertices. So the first idea is very naive, is to introduce white vertices in the middle of each edge. So we take an edge and we split it in two edges by adding a white vertex in the middle. So a priori this satisfies all the condition that this is a bipartite and it has faces which are colored. The second thing to do is to color all the type 2 edges. So we can check that these edges colored in red are actually of type 2 and the other ones are of type 1. And then what we do is just to delete all type 2 edges which are incident to a marked face. So here we have a marked face, and this is the type 2 edge incident to it, so just delete it. And these two steps are a one-to-one bijection. So this hypermaps with marked face are in bijection with bipartite maps with colored faces and with some conditions. And the condition is that all white vertices have degree 1 or 2. And the second condition is that white vertices of degree 2 are incident to 2 faces of different colors. So this is a very innocent bijection between the two sets. And then the next step will be to delete all edges of type 2. So what happens if you delete all the edges of type 2, so these are represented here in red? We will obtain star maps. So what I call star maps are maps for which all white vertices have degree 1. So now what we know is that, so in these two steps we have bijections. So we know that the coefficient G indexed by pi, mu, and nu for alpha equals 1 counts exactly these hypermaps. So hypermaps with marked faces and which has profile pi, mu, and nu. So we have a bijection. We know that they also count these maps. So now to pass from here to here, what we do is we start from this star map, we add some edges. First we add edges and then we color the faces in such a way that all the added edges are of type 2. So the conclusion of all this is that the coefficient G counts all the ways of starting from the pi star map, and then here pi is the face type of this partition, the face type of this map. So what you are saying here is that since these are star maps, so each black vertex corresponds exactly to one face. So the partition of black vertices is exactly the partition of faces, except that the partition of black vertices have not changed passing from this map to this map. We have just divided the degree by 2, but the degree of black vertices here is defined by dividing by 2, so it's exactly the same partition. So the pi from which we have started here, we will also find it here. So the conclusion is that this coefficient G, they count all the ways of adding edges on this star map and coloring faces such that the added edges are of type 2 and such that the lambda plus partition here is mu and the lambda minus partition is mu. So somehow this gives a way of interpreting the action of this operator G, but only on star maps, which is not very interesting because for now we have the feeling that there is nothing which is really happening. So the idea is that this action is exactly equivalent on star maps or any other type of maps. So the idea is to say that this coefficient G also counts the number of ways of starting from any map, not necessarily star map, but which has face partition pi, and then adding edges and coloring faces to have this condition. So the idea is to say that these two operations, they do not depend really on the structure of the map, but only on the face partition of the map, which I will try to explain now. So let's say that we start from two maps. We have two maps which have the same face partition. So here we have a star map, and here we have just another map. And the only thing in common between the two of them is that they have the same face partition. So here we have a face of degree 3 and a face of degree 2, and this is the same thing here. So this is outside face of degree 3 and the inside face of degree 2. And what we are saying is that if we have a way of adding edges here, we can copy it in exactly the same way on the right-hand side. So how does this work? The first thing, since the two faces have since the two maps have the same faces, we can define a kind of a face isomorphism between the two of them. So it's just labels on the corners of the map. But here, if we travel in some direction in this map, let's say in the direct or the clockwise, we see the labels N1, B1, N2, B2. And this is exactly what we see here. So it's N1, B1, N2, B2. So this is an isomorphism which keeps track or which respects the structure of faces between the two maps. So now, each time I add an edge here, we can just copy the same thing here. So here we have an edge between the corners B3 and N4. We'll add it between B3 and N4. Can do the same thing. So we have an edge between N1 and B5, add an edge between N1 and B5. And once we have this, it's not very hard to check that the two obtained maps have the same face degrees. And in particular, we have the same ways of coloring faces. So if I color here, for example, this face with plus, we have an exactly same face here to color with plus. So in particular, the conclusion of all this is that acting on the star map is exactly the same thing as acting on any other map with the same face partition. So in particular, we have a combinatorial interpretation of the action of this operator G on any map, which I will try to schematize here. So we have this big ellipse which represents some map M. And then we act by this operator G on this weight, which contains just the face weight with and the size weight with some normalization. And acting by G, what we do is we add some edges, very schematically colored with this big edge here, which colored in red to say that it's E of type 2. So first we add some edges, we color faces such that the added edges are of color 2. And the obtained weights here, so Q will contain the information of the weights of plus faces and R the information of minus faces. And this is exactly the action of the operator G. So now we have this combinatorial interpretation. And actually, once we have this object, the combinatorial interpretation becomes more or less easy because we know how to act by the operator CL. So we have a map, we add a black vertex with some new white vertices, precisely L white vertices, and the black vertex can be incident to some old white vertices. So let's try to understand each one of the two hand sides of this equation. So on the left-hand side, we start from, we fix a bipartite map, which is orientable, and we act by this operator G. So we know that this corresponds to adding an edge. So the first thing is we act by G. So we add some edges, we color faces so that the edges are of color of type 2. And the second step is to act by CL of Q or CL of R. So if we act by CL of Q, remember that Q is the alphabet which is related to the plus faces. So acting by CL of Q is adding this block of one black vertex on the plus side. CLR will do exactly the same thing on the minus side. And this sum of two maps corresponds exactly to this left-hand side of the equation. Which happens in the right-hand side is more interesting because we first add this vertex, this black vertex, and L new white vertices. And then we add the type 2 vertices and we color faces. So what we can obtain is something like this, in which this added vertex is completely on the plus side. It can also be completely on the minus side, but things may be more complicated. We can have some part in the plus side and some part in the minus side, except that there is some inclusion-exclusion argument, which is related to the fact that we have minus t here. So each time we add edge with a minus, and all these kind of maps, they just cancel out, and we obtain just this these maps for which the black vertex is either on the plus, completely on the plus side, or the black minus side. And this finished very briefly the combinatorial proof of this differential equation. So in the remaining 2 minutes, I will try to talk about another motivation of this differential equation, which is this conjecture, basically the conjecture of Goulden and Jackson, and slightly generalized by Schniade in 2019, which says that these structural coefficients of Jack characters, they are polynomials with non-negative and integer coefficients, not in the parameter alpha, but in the parameter b, which is alpha minus 1. And as I said, when we take the case 3 partitions have the same size, these coefficients g are the coefficient c of the matching Jack conjecture. So somehow this is a generalization of the matching Jack conjecture of Goulden and Jackson. And what we know is that about this conjecture is that we have the polynomiality part, that these coefficients are polynomial basically by the work of Dołęga and Ferré. And then in the previous work, I proved the integrality, and the positivity is always open. So my first motivation to study these differential equations was to prove the positivity in this conjecture, which was not very successful because I managed to resolve the differential equation to obtain a formula for the structural coefficient g for general alpha. And what we have in the right-hand side is some coefficients a, which has some differential definition. So they are defined with this differential c. But what is more interesting is that we know that the operator c, they construct map. So these coefficients a and the coefficient d also, they have a combinatorial interpretation in terms of non-orientable maps with non-orientability weight. Except that this formula, as you can see, a lot of signs. So this does not imply at least it does not imply directly the fact that the g are positive in the parameter b. So I suppose that there is still work to understand in a better way the combinatorics of this operator c in order to obtain from this formula positivity of the coefficient g. I will just finish with some particular cases when we look at the first terms of the operator g. So when we expand it in the parameter t, so the parameter t in the sense of the operator g is keeps track of the number of edges that we add. When you think of g as an operator which adds edges on bipartite maps and color faces. So g0, for example, it does not add any edge, it just color faces. So each time you have a face PL, you can decide to color it plus, so we'll have a weight QI, or minus, we have a weight RI. And then G1 just adds one edge and then color the face. We have this reasonable expression, and then for G2 it becomes much more complicated. But these not very nice formulas have the advantage of being positive. So in particular, give the positivity in Schneider's conjecture for the top terms where the size of pi is big enough to enter in these 3 cases. So I think I will stop here. Thank you.
Thank you, Houcine, for this very nice talk. Are there questions from the audience? So
I have one.
Victor, you have a question?
What's the reason behind the fact that you cannot extend the combinatorial proof for generic alpha, like by trying to mimic for what Chapuis and Dołęga did, for example?
Yes. So this is a very good question. So it's even more complicated than that because I was not successful to give the same proof in the non-orientable case.
Okay.
So even we don't have a non-orientability weight, but just non-orientable maps. And the reason is that, so there are 2 ways, I think, to explain it. The first way is to say that this definition of types does not work exactly the same in the non-orientable case because we have this direct orientation that we do not have in the non-orientable case. And the other, I think, maybe more deep reason is that this inclusion-exclusion here, each time you have arguments of inclusion-exclusion, they, as you explained in your talk, they behave very badly with the non-orientability weight, because the non-orientability weight really depends on the ways of adding edges. So if we try to add edges in different ways, for example, first on the plus side and then on the minus side. So there is no reason that we will have the same orientability weight, and the inclusion-exclusion argument, it does not work.
Okay, thank you.
So my question is maybe these maps where you have possible, like you have bipartite vertices and also colors on your faces, will only appear as like intermediate steps to prove some
Yes.
Identities, because the fact that you allow for like possibly adjacent faces of the same color, it kind of looks, well, it's the Ising model basically. So I was kind of wondering if there might be a deeper connection with stuff on the Ising model, but it seems that you only use them as tools in the middle of your proof.
Yes, yes, that's also the impression that I have. So it really reminds me of the Ising model, and somehow it's just an intuition that, so these bipartite maps or the hypermaps, which we have just colors on faces or on edge on faces or on vertices, they're kind of the perfect objects that we'd like to obtain by the end. But when we are studying these differential operators to what is going on in between the starting map and the final one is much more complicated. And for some magic reasons, by the end, everything cancels out and you just end up with some perfect objects, which does not really have to be the only objects which appear in the intermediate steps.
Well, I guess it's kind of a general phenomenon. Like, for instance, if you sometimes when you look at tight equations, you have to allow for like more complicated boundary conditions than the one you're actually interested in, or stuff like that.
Exactly.
Yeah, but for in this instance, it's kind of an interesting model in and of itself. So I was wondering if it played a deeper role than what you showed, but like.
Yeah, I don't know. I just remember that once my advisor told me that there are some combinatorial interpretation of some KP equations in which appear some maps like this, but I'm not very familiar with.
Well, you have, I mean, you have tau functions for KP and Toda, also for bipartite maps, and then you can kind of map that to some instances of the Ising model, but yeah, I don't think there's anything like more developed than that has been done for now. But yeah, it was very interesting questions. So related to Victor's question, so do you have any hope that you might have, at least for the alpha equals 2 case, an other combinatorial explanation, like, or a strategy to still make it work? Because it's kind of frustrating that
yes, it's frustrating because
doesn't work.
So actually there are other combinatorial interpretation of this operator CL which come from Ukachevich paths.
Oh, yeah.
Maybe if you prefer maps, this is not very satisfactory answer to your question. But yes, so there are some combinatorial identities or some commutation relations which very recently we understood that maybe it's better to understand on paths, on Ukachevich path, but the connection between these paths and maps is still very mysterious to us. It's really not very clear how to connect the two, both of them. So to answer more directly your question, I think that to have a combinatorial proof for general alpha, this is very ambitious. maybe for alpha equals 2, it's still reasonable, but for general alpha, I'm not sure that this is a good. I don't know. At least with the tools that we have now, it does not seem very feasible. And if we want, for example, to obtain positivity by the end here for this from this formula or with these operators, the idea maybe it will be more reasonable to try to understand this operator CL to try to simplify the expression which involve these operators, but only directly on the operators and not on the map level, which is from a combinatorial point of view really frustrating, but we have some reasons that maybe this B conjecture or the matching Jack conjecture of Gould and Jackson is complicated because of the complicated definition of this non-orientability weight that we have been using.
I see. Oh, thank you.
I have another question, if it's possible.
Yeah, sure.
My question is that in the differential equation you obtain, the three set of variables, they play different role because you have P on one side and QR on the other. So can this relation be interesting to generate some symmetry relation between the three parameters, or are the shape of the equation too impractical to derive such relation?
Yeah, I think this is a very good question. So this break of symmetry is somehow related to the fact that we are using structural coefficients. So somehow we have three partitions here. We have two partitions on the left-hand side, and then the partition on which we expand the product. So there is one which plays different roles, and we have some relations or some conditions on the sizes of the partition. So we break symmetry to have more or less more general objects. So yeah, that's the price to pay to have this to define this generating series. And there is also another remark that we can do exactly the same thing for constellation. So for example, when you instead of taking two partitions mu and nu, you can define theta mu1 times theta mu2 and mu k. And here we have structural coefficients which depend on k plus 1 partitions, but they still symmetric only on the k partitions on the left-hand side of the equation. And we can also have the same kind of differential equations, but instead of having Q and R here, we have Q1, Q2, and Qk. And on the hand side, on the right-hand side, we have alphabet P.
My question was more, do you think you can use this relation to, because I know that there is some symmetry relation on the Jack coefficient, for example. So do you think you could use this equation to generate new structural relation between the different coefficients? Like if you exchange the role of P and R or stuff like this?
So I don't think so, no. So the only information that you get on the, so I'm not sure that I understood very well your question. So the question was, can you get information about these coefficients?
Yes, so for example, I know that there's a relation that exists if you exchange the role of lambda and mu.
Yes, so the equations with z lambda and z mu and
yeah, exactly.
Yes.
And here it seems like you generate relation of this type between your coefficient with your differential equation. But maybe just the shape is too impractical because it seems hard to explicitly compute with this, but
yeah, I'm not sure that this is very we can use this to have this equation. I'm not sure to
okay.
The only thing I know that we can obtain some recursion formulas on this coefficient G. So we can obtain for fixed mu and nu, we can obtain G lambda mu nu from other G lambda prime mu nu for lambda prime, which is of bigger size or something like that. But to exchange the partitions, I've not thought about that.
Okay, thank you.
Thank you.
So are there any more questions? If not, let's thank Houcine again. And yeah, thank you both for these two nice talks. So this was the last session of the current thematic trimester.